Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Venu Kalari with us today. Hello, Venu.
Hi, Frank.
Let's see. And it is November 14th of 2024 as we record this. And Venu, what's your geolocation? Where are you at?
I'm located in La Serena in Chile.
Ooh, all right. So it's a complete opposite hemisphere. But we did just go through equinox. So is the weather changing a little bit?
It does in La Serena, it sort of stays the same most of the year, but it's
Oh,
getting a lot
so.
sun in the summit where the telescope is.
Hmm.
So in my paper, I'm going to talk about the Gemini Observatory, which is located around 2 hours from here,
Hmm.
and it's getting warmer in the summit because in the winter we have a lot of snow, and so now there's no snow, so we can observe more.
Very cool. That's always a good thing. Observing
Yeah.
more is always a good thing. Let's see. And so in the northern hemisphere, I'm in Phoenix, and we are definitely cooling off. We are coming into our winter season, and it's very pleasant in Phoenix in the winter. So very nice. And then what's your position there at the telescope?
I'm an assistant scientist at Gemini, so
Cool.
I do some functional work, like taking care of instruments, and some research as well.
Nice. Very cool. Very cool. And then what do you like to do for research?
I do a whole host of things for research. My favorite research topic currently is looking at star formation in external galaxies.
Nice.
So I try to look at individual stars that are just forming,
Hmm.
especially in nearby galaxies like the Magellanic Cloud, or slightly further out with more newer telescopes.
Uh-huh. Cool. Very nice. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Gemini High Resolution Optical Spectrograph Ghost at Gemini South. Instrument performance and integration, first science, and next steps. And then you take us away.
Thanks, Frank, for this opportunity. So, Gemini High Resolution Optical Spectrograph, or GHOST, as we like to call it,
Mhm.
is a new high resolution spectrograph that's just been commissioned this year. It's been functioning from this year at Gemini, and it's offered to the whole astronomical community in the US and worldwide through open access.
Cool.
To build this telescope, I would like to build this instrument. I would like to thank various teams, especially some of the primary names here. People from Australia, from the Anglo-Australian Observatory, and
Mm.
also from Canada, led by Alan McConaughey, and in Australia, led by Gordon Robertson, and also Mike Ireland at ANU, have helped build this instrument and made sure that it functions the way we'd like it to.
Awesome. Great shout out. Very cool. Okay, let's go ahead and get into it. Ghost.
So for a long time, Gemini Observatory did not have a high resolution spectrograph. And so Gemini, to give background on Gemini, Gemini has two telescopes. It's twin telescopes, one in the northern hemisphere in Hawaii at Mauna Kea, and
Yes.
one in the southern hemisphere in Cerro Patron in Chile.
Yes.
Telescope itself does not have a NASMIT platform. So these are the platforms that are used to place very big instruments, such as high resolution spectrographs or IFU units.
Yeah.
So, because of this limitation of the telescope itself, it was very hard to put a high resolution spectrograph, although there was a huge demand from the community, especially from the American astronomical community, for such a spectrograph, because there are no available high resolution spectrographs, at least in the southern hemisphere,
No.
for American astronomers, except ones that are available at ESO, which is not open access
Right.
to people based in the US.
Okay.
So to address this problem, in a long time ago, in 2010, actually, Gemini initiated a new call for community instruments. And one of the big science cases that was highlighted was a high resolution spectrograph
Yeah.
with very good blue throughput.
Mm.
This
Mm.
would address a variety of science cases, variety of high impact science cases. But they had many design challenges, as I addressed before. So to address this, there were various options explored and various proposals put forward. And the one proposal that was really successful was the one by the sorry, the name's changed a couple of times. So it's Australian Astronomical Optics now. It was Anglo-Australian Observatory before.
Okay.
So it's changed names. So apologies if I said the old name before. In collaboration with the Australian National University to build a high-resolution spectrograph.
Okay.
And this would be the way it would work is they would have a unit on the telescope itself, and this would be connected via a fiber cable all the way down to a bench spectrograph, right
Okay.
at the bottom of the actual dome of the telescope.
Okay.
The telescope, the spectrograph itself faced many problems because initially there was a contract to an external company to build the spectrograph itself. However,
Oh,
the company bailed out in 2014. So then the Canadian Herzberg Research Center stepped in.
nice.
They provided a much better spectrograph design, which had two arms, basically a blue arm and a red arm, and split at 530 nanometers, with the blue arm going up to around 360 and the red arm going around up to 1,000 nanometers. So it covered the
Nice.
whole visible wavelength range in one shot.
Cool.
So the spectrograph was built more rapidly after the Canadian team stepped in, and it was delivered to Gemini just before the start of the pandemic. So the pandemic slowed it down even more a couple of years.
A little bit, yeah.
Yeah, so after everything was relaxed, teams could come up and finally assemble the instrument and integrate it into Gemini. We began commissioning in late 2022, and we were able to offer the instrument to the community by mid 2023.
Very nice. Beautiful.
So I think the first section here is basically describing section 2 is basically describing the key requirements, the science requirements set by the community. This was a long time ago when the first white papers came out. And there were a few science cases highlighted. The main science cases I'd like to highlight are looking at abundances. So you need very high resolution spectroscopy,
Yeah.
about 20,000 spectral element resolution to look at elemental abundances. And this is very crucial because you are studying nucleosynthesis, you are studying so-called near-field cosmology. And this is a very, very high impact science case. And it helps us to understand how we try and trace back our history, so-called classically called galactic archaeology. So you're trying to dig up all elements, how did they form, and so on. A couple of more recent science cases that emerged during the building of GHOST as well was doing exoplanetary studies, basically not just looking at stars, but also planets. And this was in two ways, looking at very high precision radial velocity observation. So you get a radial velocity precision from a meter to a few tens of meters per second.
Cool.
And also another case was doing transmission spectroscopy, where GHOST can excel in because there's very high throughput and we can take long observations. But also another thing, key feature of GHOST when it's a Gemini is that we can, because Geminis operate in a queue mode, we can follow up any target very quickly. So if you have a transient that you've just discovered, and it's triggered somewhere, we can follow it up with high resolution spectroscopy, and GHOST can go as faint as 20 to 21 magnitudes in the optical. So you get really faint transients with GHOST, and not just limited to stellar and exoplanet science. One of the key cases that's emerging as GHOST right now, based on the proposals that are coming in, as looking at extragalactic systems. So it's number 5. We're looking at quasars to study the early circumgalactic medium, or to derive high precision values of fundamental constants. So these are very interesting science cases, and GHOST therefore covers the whole spectrum of science, from extragalactic object all the way down to objects in the nearby solar neighborhood.
Very nice. Beautiful. Beautiful. Okay.
Cool. Yeah. So this basically all the science cases meant that the demand from the community was to construct a very stable, very high efficiency and high resolution spectrograph that covers the whole wavelength range in the optical. So that's basically what we tried to build.
Good. Sounds like it was successful. Very cool.
Now going into the design of the instrument itself. So we
Mhm.
described the use for such an instrument. The design was complicated, as I told you, from the limitations that were set in the beginning.
Yeah.
So we couldn't just build a big bench spectrograph and mount it on an Aspen platform in Gemini. So there had to be some design, a new design incorporated. And
Okay.
so along with the high resolution bench spectrograph, there is a Cassegrain unit at Ghost, which has two small IFUs, which covers a field of view of around 7 arc minutes. And
Okay.
these IFUs can patrol anywhere in this field limited within their hemisphere. And so they are fiber bundles that transmit light from the Cassegrain all the way down to the bench spectrograph via a very high efficient fiber cable.
Hmm.
Light loss is very minimal with this design, and it also compensates for uh, air mass effects and effects due to wavelength because
Yep.
of the large wavelength range by integrating two ADCs for each IFU. So there's a mini ADC on each IFU, and this corrects for the atmospheric dispersion.
Yes. Okay.
Um,
I'm with you.
and so the final image is then transmitted via this cable all the way to the spectrograph. In figure one, you can see this schematic of how this happens. So light comes in, bouncing into the telescope, and bounces into like somewhere between 1 and 2, where the actual Cassegrain unit is. And
Hmm.
then the
Hmm.
IFUs capture this light, depending on what you want to use, either 1 or 2 IFUs, and it's transmitted by this red fiber cable all the way down to the bench spectrograph. But the spectrograph itself is very large, so you can see a man, um, a
Wow. Yeah.
6 foot man comparison, roughly, I would say.
Yeah.
Um, so it's
Mhm.
very large and it's located right at the very bottom of the telescope. But
Nice.
this also allows it to be very stable.
Oh,
So
yeah.
there's no moving parts. There's no moving parts in the telescope, and the spectrograph doesn't move that much. So it's very stable.
Yeah. You don't have to take it off and on. Very cool. Nice. Okay.
So moving ahead, this each section describes each individual part. So the main components are first the Cassegrain unit, which I described. So if you can see figure 2, I think
Yeah, sure.
that shows
Instrument modes in figure two. Let's go to figure two. Field of view.
yes. So these are very interesting figures because the three figures combined try and show how the light is transmitted. So the light enters the telescope, and the input beam is transmitted to this Cassegrain unit, which covers roughly a 7.34 arc-minute field of view. And
Mm-hmm.
there's inside that are two IFUs, each split into their own hemisphere with a minimal overlap.
Gotcha.
So
Gotcha.
each IFU can patrol this anywhere within this field. Now the IFUs can come very close to each other. I think the minimum separation is around 100 arc seconds. So
Okay.
anywhere within this field, they can go anywhere. And the great benefit of this is you can put one IFU on your target, and you can put one IFU very close to your science, very close to the sky.
Yes.
So then you can get a very good sky subtraction as well. But if you're looking at, say, a dense cluster or something, and you have two objects you'd like to look at, you can get both of them at the same time.
Very
So
nice.
there's some effective multiplexing here. So
Mm-hmm.
this light from the IFUs is transmitted, and figure 3, I think, shows the schematic of the IFU. So this is schematic of IFUs as subtended on sky. So this distance is in arcseconds. So each IFU is not just one fiber bundle. So each IFU has multiple small bundles inside of it. And
Awesome.
so the XR IFU is a standard resolution IFU. So these light transmitted into this IFU reaches a spectrograph and reaches a spectral element resolution of around 56,000. Whereas the
Cool.
high resolution one, the smaller fiber, so this is around 0.2 arcsecond,
Okay.
and this is this is transmitted into the spectrograph and reaches a spectral element resolution of 76,000. And there's
Nice.
a by sky, because the standard resolution sky allows you to get a
Mm-hmm.
uh, sky spectra really close to the science spectra as well. And there's
Cool.
also high resolution spectra, sky spectrum, which is an
Mm-hmm.
IFU too. So you can move the IFUs anywhere you want to get more sky,
I
but you
love it.
can't change the configuration of the IFUs within the actual bundle itself. So there's IFU one, you can't move the IFUs around there, but
Awesome.
you can move the two IFUs individually everywhere.
Yes. Yes. Very
So
cool. Okay.
this light is then transmitted into the spectrograph. But before it hits the spectrograph, it hits a pseudo slit unit that can be seen in figure 4.
Okay, figure 4 pseudo slit. Here we go.
So each
back off a little bit.
number here, so say this number, those numbers correspond to the number seen in figure 3.
Yes.
So you can take, so if your seeing is really good, you can see the light come in on say number 1, and then you can see that light in the actual slit as well. So you can tell if your seeing is really good, and so you can correlate the light you see and pseudo slit, and then you can also see the same schematic when you look at the actual final spectrum as well. The same applies for the high resolution slit as well. So this is arranged in such a way that there's a standard resolution object, some sky, and then another standard resolution object in the standard resolution slit, split into blue and red, because the light is split into by a dichroic and into 2 different filters. And the idea is that each filter helps you trace something for the red filter contains a lot of information for the rate of velocity of late type stars, and the blue filter contains information for more early type stars. Cool. And the idea is that this slit image can help during the reduction, the spectrum itself, to give weight to the actual spectrum reduction. So you can use this to create a weighting function that can be applied on the spectrum to know which fibers to extract and which not to extract.
Okay. Cool. Let's get a global of these 3 all at once. Let's zoom out a little bit and get the global field of view. Which probe arms and the slit. Very good. Okay, I'm with you.
So this would translate. So these numbers on the slit itself translate to the spectrum itself. So I believe there's an image of the spectrum on figure 7. So we can just skip a couple of figures and we'll come back.
Figure 7, and ooh, there we go. Flat fields.
Yes. So this is a flat field in blue and red in standard resolution, and the zoom in shows numbers, and these numbers translate directly to the numbers you see in the pseudo slit unit, and also the numbers you see in the IFU.
Okay.
So you can follow each. You can tell, okay, I've seen light in this spectrum. I can see it in the IFU. I can see it in the pseudo slit unit, and I think this is pretty neat because you can really trace where the light's coming.
Yeah.
High resolution, the image quality is not enough, that you can't separate the individual slits. But even if you look at sky in standard resolution, if you have really good seeing, you can separate the individual fibers, and you can see your object is well centered or not, or if there's something else in nearby. So we can go back to figure, I believe it would be 4 or 5.
Okay, just one sec. Okay, good. Okay, I'm with you. Figure 5. Okay, let's go to figure 5. Figure 5. Block diagrams.
Yes. Sorry, this is a bit more of the boring stuff. So
it's all good. It's all good.
Okay. So now we've described the spectrograph and the slit unit, and also the Cassegrain unit. All this information is collected via a few interfaces, and it goes into a software called the Ghost Master Process, which transmits to the Gemini interface, which then transmits to the telescope control. So all of this happens very seamlessly, and it all happens in a matter of a few seconds. So it's controlled very quickly. So if you want to, and this is very beneficial. So if you want to, say, switch instruments at night, and you want to very quickly acquire an object, it can be done within a matter of less than 5 minutes. So if you're in and you want to follow up really rapidly within 5 minutes,
nice.
Deciding to let's observe the target, you can actually be on that target. It's a very quick acquisition because of this whole scenario. Acquisition as well is very quick with Ghost. And then below is a diagram showing the actual image format. So the image comes stacked from each filter. Each amplifier.
Right. EFG and so on. H. Okay. Very cool. Okay.
So I think we can move on to more of the performance, I think.
Okay. Performance.
So Yeah, so in the performance section, this is all tests that we did during the commissioning and the integration of the instrument into telescope. And there's the performance section covers engineering tests and experiments we did to see how good the spectrograph is, how much can it perform for a variety of science cases. And one of the first things you need to know is how good can you acquire a target and how good can you guide on a target.
Yeah.
So to do this, Ghost uses a loop. So around each science IFU, there's a guide IFU. So we can go back to figure two.
Yeah, figure
Sorry.
two. Sure. All good. All good. Figure two, and there was one, sorry.
Oh, sorry, figure three it would be.
All good.
Yes.
Figure three, right? This one.
Yes. So around each science IFU, the red hexagons are
Yes.
basically the guide IFU. So light is captured from that,
Okay.
and it fits a Gaussian,
Okay.
and then it helps to recenter it. So the recentering is pretty accurate, and it recenters during the observation as well. So there's a loop. You can set the frequency of how often you want to recenter it, and so on. So each science IFU also has guide IFUs around it, which help to guide the target. You can also use blind guiding. So
Yeah.
maybe
Yeah.
you can use one of the other IFUs to guide on a very faint target
Sure.
with that. So there's multiple options possible.
Cool.
Um, so if we go back to the acquisition and guiding,
Yeah, sure. Let's slide down to the acquisition and guiding, and there we go.
yeah. So basically, this is the images from the guide camera, the guide IFUs are fit to a Gaussian, and then they control the Gaussian, and you can control when they're refreshed each time. The guide tolerance is the guide precision is pretty good. It's less than 0.05 arcseconds or something like that. So you can really precisely guide on a target. One very interesting thing, of course, is sometimes if you might not know a target where exactly to look at it, especially if you're a transient
Yeah.
that's located from another telescope and it's not very precise. So if you go into figure 6, I believe.
Okay. Figure six.
Figure
Spiral
6. So this is a schematic that shows the ghost IFU in the very center, say at 0. And so each time, so if you don't know exactly where your coordinates are, you can
Yes.
tell the instrument to start a spiral search, which sort of starts a sequence where it tries to find the very brightest spot and move there. So if your brightest spot is to the left, to the top left of the IFU, it'll move to the top left. And then I'll repeat it again. I'll repeat it again. I'll repeat it again. I'll repeat it
Okay.
again till the very brightest point is at the center of the IFU. So then you're centered on the star. And this is blind, so you don't know exactly where the target is. So it'll try and find the target, and it does it pretty
Nice.
rapidly, and it's very good for if you don't exactly know where the target is
Right.
during
And
the
for
night.
transients, often you don't. So
Yeah,
very
if for
cool.
transits, yeah. So
Very cool.
that's one of the good features of the acquisition
Yeah.
guiding. Yeah.
Very nice. I like that feature. Very cool.
So I think we can move on to section 4.2. Basically, is what was shown before in figure 7 is the spectral format. Of course, so there's two cameras, the red and the blue camera. Can I have a look at figure 7, please?
Sure. Figure 7. There we go. Flat fields.
Yes. So there's basically two cameras, the red and the blue,
Uh-huh.
different colors shown, and there's 4 amplifiers in each camera. So this is the stitched image with all the 4 amplifiers. So it also shows all the individual orders and so on.
Yes.
So that's basically a small description of the spectral format. And then section 4.3 covers the resolution. I think there's an image in figure 8 that shows the resolution of the post. Yes.
Okay, figure 8. Just getting that down a little bit. Figure 8. Let's go to figure 8.
Yeah, figures aren't very well coordinated with the section numbers, I guess.
Oh, yeah. Well, there's 24 figures in this one, so it's okay. It's all good.
Yeah.
Okay.
So these two are maps of the spectral resolution where they fall in the detector. So basically, if you can imagine figure 7, where the blue image on the top and the red image on the bottom, I believe,
Yes.
in high resolution mode, it tells you where's the resolution on each pixel. Basically, it's an
Yeah.
interpolation of different lines. You can see what the resolution was, and we interpolated it to compute like sort of resolution map. So you can see
Cool.
the best resolution is along the center, we would expect. Towards the left of the detector, the resolution lowers, and towards the right as well, it lowers, but not as much. And it's the same pattern that's found in both detectors. Makes sense. They're both from the same manufacturer and very
Yeah.
similar.
Okay.
They're just one detector is slightly bigger than the other.
Okay.
Um,
Very
so
nice.
that's the resolution. So you can hit, if you have a line right in the very center, you can hit a spectral resolution of say 75,000 in the blue and the
Easily.
red. But
Easily.
yeah, yeah. And if your line's falling more towards the left, your resolution is lower.
Uh,
So not only can Ghost
so good.
deliver very resolution, it also has a very good throughput. Its throughput is comparable to similar high resolution spectrographs such as in the Southern Hemisphere from other facilities. And it compares quite well in the blue, especially because Gemini mirror is a bit different to other telescopes mirror in that it's a silver coated primary. So the throughput in the red is very good, but the throughput in the blue lowers because of this. Um,
Yeah.
so even then, the performance in the blue is pretty good. You can get a lot of signal around 380 to 370,
Uh-huh. Uh-huh.
right target in the blue.
Uh-huh.
And the drop in the middle there is because of the dichroic. That's where the two detectors meet.
Ah, got it. Got it. Okay. Yep. Yep. And then it
Mm.
carries on, and we go on to the red until we get out of range. Very cool. And these are percentages on here. Okay. Cool.
So the throughput is also a function of the same as would be expected. So I think figure 10 shows that, shows a curve how the throughput varies, or
Transmissions.
the transmission varies as a function of seeing. But you can see in this figure as well. So IQ 20, IQ 70 refers to the percentile bins of how often we have like that image quality at Gemini.
Okay.
So IQ 85 is something roughly 1 arc second or worse. So
Mm.
that's generally 85% of the time at Gemini we get seeing of around 1 arc second or better. And
Cool.
the rest of the time we get really horrible seeing, like the other 15% of the time. But even in that situation, there is a lot of light that can come through ghosts, especially for bright objects. So you can monitor bright objects with with the instrument. You can perform monitoring campaigns, and regardless of the weather, you'll always get a spectrum. And so you can follow up objects, and that's one of the data science cases that's slowly emerging
Nice.
using the
Lovely.
of
Very nice. Okay. Cool. Nice instrument.
yeah. So section 4.5, I think, describes the performance of Ghost in regard to radial velocity. So as I described, one of the key science cases that emerged
Mm-hmm.
during the building of the instrument was following it up with detecting exoplanets with very high precision radial velocity measurements.
Mm-hmm.
The instrument itself is not built for very extreme precision radial velocities. It has a simultaneous calibration lamp, but it's not designed principally. It's not vacuum controlled. It's only pressure controlled.
Right.
So sorry, it's only temperature control. It's not pressure control. So there is some
Oh,
variation in some effect of the ambient atmosphere. But regardless, the performance seems to be pretty good
yeah.
because of the stability of the instrument. So I think there's a good description of the performance in figure 13 and 12 as well.
Okay. So let's slide
So
down to 12. Mean pixel drift.
yeah, so these two figures compare the drift with the pressure and the temperature, which is the two factors that impact the variation drifts in the spectrograph. So the drift is very small and it's
Oh,
well within the limitations of 0.1
yeah.
pixels. So that's the drift you get over a few days.
Okay.
Uh,
Okay.
and
Okay.
that can be seen, that can be translated directly into science as well. So if you look at figure 13,
Yeah.
that shows the radial velocity of one star that was followed over a 6-night duration. We do take radial velocity standards of a limited set of stars every few weeks at Gemini to keep following up the radial velocity precision
Right.
over time, the accuracy over time. But this during commissioning, we followed one star every night, and we saw how good the radial velocity measurements was. And there was a lot of variation in the temperature and the conditions. So there was this just before a storm, and this is during winter, just before and
Cool.
just after the storm, I believe.
Okay. Real
How,
life test. Mm-hmm.
yeah. So the variation is between 50 to 100 meters per second, and
Yeah.
it's very very reproducible because we did more similar tests more recently. Um,
Mm-hmm.
so it's 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 decent enough for if you want to follow up real velocities
Oh,
depending on the
absolutely.
science.
Very good. That'll make for a nice science case. Okay.
So I think figure 14 and 15 show one of the science cases. I think it's very exciting for more extragalactic astronomers.
Okay, 14. Yeah, looks like
So,
for lines.
so this is a emission line star at around 21 magnitudes in WE, and we observed it for around 2.5 hours, I believe.
Mm-hmm.
We could detect very clearly emission lines in beta and also forbidden oxygen.
Yes.
Um, so so you can technically detect
Nice.
emission lines in very faint to see profiles and so on. See if you have a P signal profile or so on and so forth. And the detection can be really realized that it's not sky in figure 15. So
Yes.
that's
Gotta make sure of that.
that's the basic 2D spectrograph, and you can see the broad H alpha line there, and you can see that that's the object, and the lines on the side are object and sky, so they're basically sky lines around H alpha line, and you can see
Right.
those lines cover the whole detector, whereas the H alpha line only is centered on the object and you can't see anything around the sky. So
Yeah.
that basically is there's no H alpha surrounding region within I think it's two arc seconds away is the sky fibers.
Okay.
So there's this is the H alpha emission comes from the source itself. Unfortunately, this is very fast rotating source, I believe. So the lines are pretty broad.
Yeah.
But if you have a narrow slow rotator or is some source where you need to look at the profiles, you can get line profiles even at very faint magnitudes, especially emission line ones.
Very nice. Very, very nice. Love it. Okay. And where were we? This was on our, okay, we did radial velocities, performance at the faint end. Then we sort of roll into first science results. Yeah.
Yes. So this is the exciting part for I guess scientists and astronomers watching it. Um, so after the instrument was commissioned, there was a lot of work that has been done by the instrument team and the commissioning team, and they've published a lot of papers, especially looking at elemental abundances in extragalactic dwarf galaxies. There's
Yes.
also been science published looking at transmission spectroscopy with ghosts and also real velocity measurements of exoplanets.
Use it all.
Uh, so there's a lot of interesting science that's coming out already, and we hope that a lot more science comes out. In this section, we describe like a few science cases that have to highlight a few science cases. One of the classic ones at Gemini, at least, is PIs requesting a variety of objects to follow up. And so here we've put in an example of a very, very interesting star called XX of Ophiuchus. This is a one of two known iron stars. So the other one is AS325. These are stars that have a lot of emission lines in their spectra and a lot of P Cygni profiles, and we believe there's a binary, the late type star, and an early type star. So we took spectra of these stars basically to look at them, and I think it was a bit confusing because when we first looked at the spectra, we thought something was wrong. One of the people involved in the reduction thought there was something wrong with the spectrograph because there was a lot of emission lines, and they're like, "Oh, there's something going on." And we were like, "No, no, actually, that's what the spectrum looks like."
Yes, yeah.
Um, yeah, so you can have a look at the variety of the line profiles. There's a lot more detail here, and you can look at the detail. Zoom up the H alpha line in image B on the zoom.
Right.
Yeah, so you can see like all the details.
Wow.
There's a lot of detail that can be seen,
Wow.
especially for a spectrum like this, because
Wow.
it's filled with emission lines and a few absorption lights here and there. So it's very nice to see
Oh, it's got
the
great resolution.
resolution.
Yeah, it's
Yeah,
got spectral resolution. Really nice. Uh-huh. This goes all the way back to Merrill. Yes.
yeah,
Very.
that's one of the reasons why I think the star was targeted, isn't it? It's
Yeah.
historic.
I don't think Merrill made the observations, but I get it. Very
Probably
good.
not.
Very cool. Okay, then we get into some lighter stuff from iron to lithium here in TW Hydra.
Yeah, so TW Hydra, as some of you may know, is one of the well-known pre-main sequence stars.
Yeah.
It ages around 8 to 10 million years, and there's a lot of debate about its age because it's thought to be too old to be a pre-main sequence star.
Yes.
But it only has lithium within it. And we looked at lithium not just in the classic 6708 line, but also in another line which can be seen in figure 18.
Yeah,
There's
let's take a
the
look. Ooh.
at
Maybe that's
6103.
17.
There's another lithium
17.
line.
You want this one, 17? This is for TW Hydra.
Oh, this is TW Hydra. So this is a quick look plot that can be generated with the spectra. So it's showing the whole
Wow.
wavelength range, right from 360 down to 1,000
Got it. They
nanometers,
roll. Okay. Okay.
shaded by approximately what the color would be to the human eye, I guess.
Yeah.
There's a lot of debate about what color we should use where, but I assume like the ultraviolet is violet and the red is red.
Yeah, I don't think we're
I
gonna see
remember discussing a lot
many
with
green
Nicholas.
stars there, but okay, very good.
Yeah, we snuck in some green there. I mean,
It's all good. That's
yeah.
a lovely spectrum. I mean, that's just really great. That is very cool.
And you can see all the emission lines as well in the Balmer lines showing
Yeah.
signatures in TW Hydra.
Mm-hmm. Very cool.
This is not corrected for telluric, so you can see this. You can measure the resolution with the telluric lines, I assume. So that's one factor of it. Yes.
Yes. Yes. Nice. Okay. Absorb that beautiful spectrum, people. 17 and TW Hydra. Did we want to go to 18? Yeah, this is still TW Hydra.
So this also demonstrates the resolution. So there's a lithium line around 6104
Yes.
nanometer, 6104 Armstrongs, and that can be well separated from the nearby calcium line and the 2Fe line. So that can give you an elemental abundance, which agrees with the elemental abundance from the classic 6708 Armstrong lithium line. So that's heartening to see. And that's one of the signs to demonstrate we can do such we can resolve such lines with. Of course, and that's one of the main reasons this was exemplified.
Very cool. Okay, we go from 2, and we slide into faint stuff. All right, quasar.
Yes, so this target was observed to highlight some of the extragalactic science that can be done with GOES. So this is a target that was observed as part of the DAISY survey. So there would be already.
Oh, okay, yeah.
This is a survey that takes spectra at low resolution.
3000. Yep.
So there would be a spectra to compare flux spectra and see how well GOES performs for the flux calibration and what's the impact of resolution we can see here. So I think the next figure, 20, shows that. So there's an overlay
both
of the GOES.
Cover both. We'll just cover both. Here we go. 19 and 20.
So 20 shows the DAISY spectrum and also an SDSS spectrum overlaid on the GOES spectrum. So you can see the impact of the feature, the higher resolution. You can separate a lot more lines, especially in the Lyman alpha forest.
Yeah.
And the same when you look at the flux calibrated spectrum, they're covering the whole wavelength range. So you can see the Lyman alpha forest. You can separate lines. You can get abundances, line widths, and so on. So this is one of the key science cases for GOES measuring extragalactic abundances.
Wow. Spectacular resolution. Spectacular.
Yeah.
Good job. Okay. Wow. And these are faint.
Yeah, I think this is around 18 magnitudes.
Yeah, thereabouts. Very cool.
So it was observed in R&R, so that you can go fainter if you take a longer exposure.
Sure.
Basically, you can take 1 hour exposure. You can go like 18 or 19 very easily.
Beautiful. Okay. So we got elements, we got faint targets. How about time series? Let's do some time series.
Yeah, so this is more science that I'm not that familiar with. Basically, the idea is to look at we'll be looking at the radial velocity stability But also we were trying to ask people, are you interested in observing exoplanets to look at exoplanet detection? So this was done by one of our Brazilian collaborators, Eder Maritoli, and he looked at a transit of an object, a transit of a planet, but also I think it was a very cool idea is to follow up a standard star with other IFU. So you're looking at transit with one IFU, and the
Oh,
other is on a standard star. So you can sort of get a baseline to compare the transit to, and sort of that's the more interesting thing
yeah.
that can be done with Ghost, not just exoplanet transit, but you can also not only can you have good precision rate velocities, but you can also follow it up with a standard star.
Yeah,
Same,
cool.
they can simultaneously. So I think there's a measurement of the CCFs and the residuals, but also following the red and the blue, um, the full width half max, and also the delta in figure 22, I think it would be, seeing the variation,
22. Yeah, let's go over there.
seeing the variation of RV over time and what's the effect of it. So this displayed that Ghost can detect exoplanet transits, but also one can
Oh,
use
lovely.
a
Okay.
standard star.
Yeah, I'm with you. Okay, blue channel, red channel. Dot, 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 dot. Okay. Your mouse is changing. Good. Wow, very cool. Nice. Okay. So we can do timing.
Yeah.
Cool. Okay. Let's go in. So we got that. We got faint stuff. Poor weather observations. That's always fun.
Yeah, so this is what I was describing before. So a fraction of the time at any observatory, you get really horrible weather. I
Yeah.
mean, a Gemini it's 1 hour second above. We call it to be poor weather, but you can have really a lot of clouds, even in good seeing, or like a lot of wind or so on.
Yes.
And depending on all of this, in a lot of clouds and poor seeing, you can still observe a lot of targets, especially with
Mhm.
GOES, because it's an 8 meter telescope. And you can get a lot of information because it's high resolution spectrograph. So it's very useful for science, and you
Oh,
can do
yes.
some of the science with it. So in horrible conditions, so there's a lot of cloud around more than 1 arcsecond seeing. We observed our Lyra star, and we tried to look at the line profiles of it. And we've followed this up by taking more observations of the same star to look at
Yes.
the change in rate of velocity and so on.
Oh, good.
So
Okay.
in figure 23, you can see line profiles of the Lyra star.
3. Okay. Okay, I'm with you. 23. Okay. And doubling of the H alpha and H epsilon. There we go. H alpha, beta, delta, epsilon. Very cool.
Yeah, so this is just an example of what you can do in poor weather. So you don't need to be restricted to really good conditions to get great spectra, especially for bright objects. If you want to
Yeah.
follow up stars, there's a lot of science that can be done
Okay.
in that situation.
Very cool. So a little weather immunity, somewhat.
Yeah, that's a good way to put it.
Weather immunity. I'll make a vaccine or something like that. I don't know. Okay. It's 23. And we're going to hold off here on next steps for a moment. Yeah, we'll hang off on that. So very cool. Venu, I want to thank you so much for walking us through this broad discussion of this awesome new instrument at Gemini, Ghost. Very cool. Thank you.
Thank you.
Let's see. And of course, I'm leaving a little bit here to the end. Of course, it was in the title, next steps. And so let's go ahead and cover that at this point. And so what are the next steps with Ghost, and where may it evolve to, and other science cases and so on? So where do we go from here on the next steps?
So Ghost when it was designed and commissioned, it had envisaged 3 different modes. One was the standard resolution mode and the high resolution mode. They're both commissioned and they're offered in all ways and forms to the community. So
Cool.
anyone can apply for time and as part of the US Open Skies policy, and we encourage anyone to apply for time, especially from the US astronomical community. Gemini has a variety of ways where you can get time. But the next steps for GHOST in particular are the precision radial velocity. So that's the third mode of GHOST that emerged during the building
Okay.
of the instrument. And
Okay.
so GHOST itself has a simultaneous calibration unit that
Mhm.
allows light to be thrown into the instrument, and that light falls beneath the sine spectra as one fiber. So
Okay.
if you can envisage the figure that was shown before, the spectral format,
Yeah.
below all of that, there's one fiber for each order that covers a simultaneous calibration unit. So that can be used in real time and only in high resolution mode to get more precision radial velocities. We've done a lot of testing with that mode, and we were able to show that we could do we can achieve precision radial velocities between 1 to 10 meters per second, depending on a variety of factors. So now currently work is undergoing at Gemini to add small software so that observers and PIs can use this mode, but also we're doing more observations to establish the precision of the radial velocity we can deliver.
Cool. Well, it'll be really exciting to see this instrument get used over the next couple of years and the various science cases that come out of it. It's an awesome addition to the field. So very cool.
Thank you, Frank.
Yeah, be great. And that will do, everyone. And I hope this made your Ghost Astronomy Day just a little bit better. And we will see you on the next one. Bye-bye.
Bye. Thank you.